We're continuing in 7-3 on a discussion concerning capacitors, and we're looking at current flow in a capacitive circuit. Even though a capacitor has an internal insulator, okay, and that's going to be right here, current can flow through the external circuit as long as the capacitor is charging and discharging. So as long as it's charging and discharging, current can flow. Now you may recall that in the previous discussion we had our capacitor connected to a DC source, and with DC, remember, current is only going in one direction. So once the capacitor was charged, then current ceased to move in that circuit at all, and it opposed the source and there was no movement. Now with AC, it's a little bit different, because with AC we have a signal that's going positive and then it's going negative. And so what will happen is when the circuit goes positive, the charge on the capacitor will be a positive charge, and when the AC signal goes in the negative direction, the capacitor will discharge, and then it will charge it with the opposite polarity. And so the charge will be, or the capacitor will be constantly charging and discharging. And so current will continue to move in the external circuit with an AC signal source. Now remember that current does not go through the cap. Another point of discussion concerning movement of current: an open circuit forms an accidental capacitance that charges to the value of the applied voltage. Now you may recall when we looked at DC circuits, okay, we looked at DC circuits, and you may recall that we connected components up, and I'm going to put in a few resistors here. And one of the things that we found was that when we had an open circuit, and I purposely didn't connect this, when we had an open circuit and we went in here with our voltmeter and we connected across the 2 points of our open, we found that we had the supply voltage was felt right here. And one of the reasons that we had that was that remember that we had to have a complete circuit for current to flow. And when there was no voltage drop across these components, then there was no current flowing through them, then there was no voltage drop. And so when we measured here, we felt the supply voltage. Another way to look at that is this is an accidental capacitance, because here remember that air can operate as a capacitor. Now the end of the wire is going to be an extremely small plate area, but you can view this as an accidental capacitance, and then you see the applied voltage. Now the thing is that when you take the voltage away, this capacitor is not going to hold it very long, just because the plate area is so small and the distance between the plates is probably so large. But at any rate, this can be viewed as an accidental capacitance. Okay, capacitive reactance. The value of current in a capacitive circuit with an AC source is directly proportional to the value of the capacitor. Current is also directly proportional to frequency, meaning the cap has to charge more times per second. Opposition to current flow due to the charging and discharging of the plates is referred to as capacitive reactance, and it is calculated like this: 1 over 2 pi times frequency times capacitance. And this value, like with inductive reactance, is measured in ohms. Only thing is that remember when we calculated inductive reactance, remember X of L, we said we had 2 pi times frequency times inductance. And so in this case we have this very similar form, except it's 1 over that value, and we replace C with L. But at any rate, they both represent opposition to current, and they are measured in ohms. Okay, capacitive reactance. Here's our formula again, and we're going to calculate what is the capacitive reactance offered to a 20 microfarad cap when in a 60 hertz circuit and then in a 200 hertz circuit. So here we have our formula. Here we're calculating with 60 hertz, and we result with 132.6 ohms. We increase the frequency, and notice what happens to the resistance, that it actually goes down. If we had been dealing with inductance, it would have gone up. The higher the frequency, the more reactance. In this case, the higher the frequency, the lower the reactance, and you can see that when F is in the denominator, the higher F goes, the lower the reactance. Notice, like inductive reactance, capacitive reactance is a function of frequency, but they are inverses of each other. With inductive reactance, as frequency goes up, reactance goes up, but with capacitors, as frequency goes up, reactance goes down. Okay, capacitor types. There are many ways to categorize capacitors and distinguish between them. So we're going to categorize them with three different methods: by the lead style, fixed and variable, and polarized and non-polarized. And so for these first two, I do want you to take a look at your book. Lead styles, there's some nice pictures there of aerial, radio, and they're different lead styles. You know, sometimes you see them like this, and sometimes you see them like this, and sometimes they're surface mounted, but please refer to your text for some pictures. Then there are fixed and variable, and this just has to do with like resistors and inductors. Capacitors can be of a fixed value, or they can be variable, and again, please see your text for some pictures of those. Then we have polarized and non-polarized capacitors. Polarized capacitors must be inserted into the circuit according to the polarity marked on the capacitor, and usually you'll see a plus or a minus on the capacitor if it is of the polarized type. If placed in the circuit incorrectly, they can and do explode. So great caution should be exercised when placing polarized caps in the circuit, and I have seen many of these explode. Kind of embarrassing for the person putting in the circuit in the lab. They go in there and they blow up. Everybody thinks, oh my, capacitor in backwards. So oftentimes people learn this, but there is a hazard involved, so ensure that when you put them in the circuit, you're putting them in correctly. Non-polarized capacitors can be placed in a circuit in either direction. So non-polarized don't care, but of the polarized variety, you must use caution. Okay, capacitors are rated according to three features, and this we're going to be looking at capacitance, voltage, and temperature coefficient. The first is capacitance, and this is where you would see, you know, where it's rated as 400 microfarad, or I don't know, 0.1 microfarad, or whatever. They also have an associated tolerance, like with resistors you might see 5% or whatever. They have a variety of tolerances associated with them. Voltage indicates the maximum voltage that can be applied to the capacitor without damaging the circuit. And oftentimes you'll see, for example, 100 or 250 or 400, just a few of the values you might see. Then there is the temperature coefficient. This addresses how the value of the capacitor will change under the influence of heat. It addresses polarity and magnitude. So this addresses how the value of the capacitor is going to change under the influence of heat. And so two things we're going to look at: polarity and magnitude. Polarity has to do with, well, does the capacitance go up or does it go down with the influence of heat? Because there are different types of capacitors, can go either way. Then the magnitude, it tells how much the capacitance value changes for a given temperature. And this is given in parts per million per degree centigrade. Temperature coefficient information is provided by manufacturer data sheets and usually not written on the capacitor. And capacitor technologies. In this particular section, I'm not going to lecture. I want just to refer you to your text because your text has some nice pictures associated with different capacitor technologies. So please do read that section from your textbook.